Hello there. Welcome to my channel. My name is Eric, and in this series, we are going to build a mini machine learning framework from scratch. Our final goal is to implement backpropagation over a dynamically built computation graph of scalar values. On top of that, we will build a multi-layer perceptron and be able to optimize it using backpropagation. This project takes inspiration from Andrei Karpathy's micrograd project, but we will be using Rust programming language. When completed, it will be about a few hundred lines of code. This piece of code demonstrates what you would expect to finish at the end of this series. In this code, NN is an instance of the multi-layer perceptron with two input neurons, and the architecture is defined by the array 3, 1, meaning the MLP has one hidden layer with 3 neurons and one output neuron. XS is a vector representing the input sample of our training dataset. In this case, it is comprised of two floating point values, 1 and -1. YS is the corresponding ground truth output that our MLP should ideally learn to predict. LR is the learning rate. This value represents the step size at which the neural network adjusts its parameters during the training process. Loss is a placeholder for the loss value, initialized at 0. Its value is updated in each iteration of the training loop to represent how far off our model's prediction is from the true output. N iter defines the total number of training iterations. Inside the iteration, Y is the current prediction of our MLP when applied to XS. Diff holds the difference between the predicted output Y and the ground truth YS. This difference is then squared, and the result is stored in the loss, which represents our model's performance. We then print the current loss value to keep track of the training process. We calculate the gradient of the loss function with calculate grad. This gradient will be used in the parameter update step. We loop through each learnable parameter of our MLP, multiplying its gradient by the learning rate and subtracting this product from the current parameter value. This is the essence of our gradient descent optimization method that enables our MLP to learn from the data. Let's execute the demo code. Keep in mind that the primary goal here is to minimize the loss. As the code runs, you will observe the value of loss being printed for each iteration. This iterative process continues until the loss becomes smaller than our set threshold. As we can see, the loss keeps decreasing with every iteration. That's exactly what we are aiming for. This decrease in loss signifies that our neural network is adjusting its learnable parameters effectively. This adjustment helps in reducing the difference between the network's output prediction and the actual ground truth. In other words, our network is gradually learning and improving its predicting power. Exciting times ahead. It is time we delve into the crux of this episode. The core goal is to lay the essential groundwork by building a computation graph. In particular, we are going to focus on implementing the value data structure and also several mathematical operations that are frequently used in neural networks. On top of that, unit tests will be added to ensure the proper functioning of our implementations. In accomplishing these tasks, we will be exploring some fundamental Rust concepts, specifically smart pointers. We will become familiar with the concepts such as reference counting and interior mutability, which are crucial for efficient memory management and avoiding data races. Enum. We will be using enums to construct algebraic data types. These are incredibly useful for constructing values, which can be one of several different but fixed types. Math operations traits. Traits are essentially interfaces in Rust. Here, we will be implementing traits to perform mathematical operations, which can help to make our code cleaner and more modular. Atomic data types. These types allow for log-free concurrent programming, ensuring data integrity in multi-thread scenarios. At the core of our graph lies the fundamental value struct. This structure serves as the building blocks of our computation graph. It has primarily two roles. First, a value can represent a constant. This is typically utilized when dealing with training data and features which do not change during the learning process. Second, a value can also serve as a variable that changes in the course of training. For example, it can represent the weights and the biases of a neural network that are continuously updated during training. Therefore, our value struct should support mutation after initialization. The value struct should be able to perform a variety of mathematical operations and produce a new value as a product. Furthermore, an instance of value must be reusable, meaning it should be capable of performing mathematical operations with multiple other value instances. This would allow a single value to take part in many computations, a necessary requirement in complex graphs where many interacted operations occur. So we have clarified the value data type. Next, let's talk about how to combine them to build a neural network. A neural network is essentially a directed acyclic graph that requires mutation. This brings us face to face with two chief problems in Rust: mutability and lifetime management. On the mutability front, we have two primary options. We can use raw pointers. It offers a lot of flexibility. However, they also introduce the potential for unsafe code, which tends to negate the benefits of Rust safety guarantees. On the other hand, we can also use interior mutability. Although it provides a safety net around the mutation by wrapping it inside a safe API, it can be relatively verbose to write. When it comes to lifetime management, we also have two options. Reference counting. This strategy does present a risk of memory leaks if the graph has cycles. However, this won't be a concern for us, as neural networks are typically represented as acyclic graphs. For lifetime management, we can also use arena allocation. This method uses borrowed references and thus may need to use unsafe Rust code. Consequent to these considerations, we have decided to use a combination of interior mutability and reference counting. This combination allows for safe mutable access to shared data, along with effective lifetime management. I highly recommend checking out the blog post, Graphs and Arena Allocation. It is an exceptional resource that has been instrumental in helping me making these decisions. All right, we have laid the theoretical groundwork. Now, let's turn our attention towards some practical implementation. Our core data structure consists of value and value underscore. The value underscore holds all the essential fields, while the value is actually a wrapper of value underscore with a reference count. Structuring our code in this way helps value instances to be lightweight when it comes to cloning, because RC only increments the reference count during cloning rather than duplicating the whole data. We can easily and efficiently reuse value in different mathematical operations. Here, the value struct is a tuple struct that has only one entry. This pattern is very pervasive in Rust, and it has its own name, the new type pattern. For details, I recommend checking out item 7 from the Effective Rust book. We begin by defining four main fields inside the value underscore. ID. This is an unsigned integer used to uniquely identify each value underscore instance. Data. This field encapsulates the current numerical representation of value underscore. Given its mutable nature, this field is wrapped in refcell, a smart pointer that enforces borrow rules at runtime instead of compile time, thus providing interior mutability of the field. Grad. This is the gradient or derivative of the loss with respect to this value underscore. This provides crucial information for updating our network's weights during backpropagation. Similar to data, grad is liable to update and thus is also wrapped in refcell. For simplicity, both data and grad are defined as a 32-bit floating point numbers, suitable for most computations in machine learning. Lastly, we have the operation field. It is an enum embracing the different mathematical operations that can generate this value. This operation is at the core of how a neural network propagates input, processes it, and updates itself. Now let's define the enum op. Firstly, we will have only one case. The op is equal to none. That means the value is initialized directly from data. In other cases, the value can be computed from mathematical operations. In our previous step, we defined some fundamental data models. The next step is to implement methods that will manipulate these data models. Let's get started by implementing the new method. This method takes a one parameter of F32 type and will subsequently return a new value underscore. The data shall be wrapped inside a ref cell. Since this is a new instance, the gradient should be set to 0 initially. Because we are initializing this instance directly from data, not through any mathematical operations, the operation or the op field will be set to none. So what about the ID for each new instance? We need it to be unique, which means that we may need a function that can return sequential unique IDs. For now, let's use getID as a placeholder. As for implementing the getID method, in my first attempt, I was trying to use the static global mutable variable. For example, and then within the getID method, the global variable is incremented by 1 and gets returned. However, as the compiler points out, this approach requires using unsafe raster code. This approach is not thread safe. There can be data races if the getID is invoked from multi-threads concurrently. To address the issue, I opted to use atomic type, specifically atomic usize. In the revised getID method, we called fetchAdd on the atomic usize. This method is going to add to the current value and returning the previous value. So ID is initialized as 0. The first time getID is invoked, it returns 0, and the second time it returns 1. This approach, we avoid using unsafe code, and it is also thread safe. Let's also implement a getter method to get the current data. Because data is wrapped inside a ref cell, it would be too verbose to use the borrow method to get the inner value. The implementation is quite straightforward. However, what if we also want to get the current data from the value? It is not ideal to re-implement the code in value. So here we can apply the trick to implement deref trait on value. That would allow us to treat smart pointer, which is RC, as normal reference. For details, please check out chapter 15, section 2 in the book, The Rust Programming Language. The implementation is not complex. The method takes one parameter, which is an immutable reference to value, and returns an immutable reference to value underscore. Finally, let's also implement the new method to create a new value instance. With these utility methods now in place, it is a good practice to write some unit tests to check whether everything is functioning as expected. In our unit test, we will create a new value instance with data set to 0 0.5. Then we will verify if the getData method properly returns the value of 0 0.5. Our unit test passes successfully, which confirms that the code for creating a new value and retrieving data through deref coercion is indeed working as intended. Now that we have defined our core data structures, value and value underscore, let's move on to implement several essential mathematical operations. Each operation plays a crucial role in different aspects of neural network computations. First is the add operation. It takes two parameters. This operation is used to combine two values in various scenarios within a neural network, from combining inputs to adding bias terms. Then is the sub. The subtraction operation serves a key role in calculating the loss of our neural network. This operation enables us to quantify the difference between the predicted results and the ground truth values. The smaller this difference, the better the prediction. Then MUL, multiplication. This is commonly used to adjust the input signals by weights during the forward pass in neural networks. Finally is the tanh. This operation is used as an activation function, introducing nonlinearity into the neural network's computations. These nonlinear transformations allow the model to learn and model complex patterns in the input data. In our previous discussions, we covered the various mathematical operations and their normal functionalities within a neural network. Now it's time to implement these operations. Some operations, like add, multiplication, and subtraction, can be implemented through the mathematical traits, but others may not have the corresponding trait. In such cases, these operations can be implemented as methods of the value struct. To start with, let's implement the add operation. To achieve this, we will use the stdops add from the Rust standard library. With this trait, when we try to add new value instances together, it will be used implicitly. The implementation of add operation requires you to specify the output type, which in our case is nothing but value. After this, you need to implement the add function. In the add function, we first define data as a result of adding the right-hand side and the left-hand side. Next, we create a new value underscore instance with the data value. Then, we create an op add enum, setting the first and the second fields with the left-hand side and the right-hand side. It is important to mention here that both left-hand side and right-hand side needs to be clonable. This is accomplished by adding the derive clone attribute to our value struct. Let's also implement the unit test to make sure the implementation of add operation is correct. Here, I define the V2 with the data equal to 0.3, and V3 is equal to V1 plus V2. Then I verify if the data from V3 is equal to 0.8, which is expected to be from 0.5 plus 0.3. The test passed. That means our implementation of the add operation is working. Implementing multiplication and subtraction operations follow an approach similar to what we use for the add operation. The core differences lies in how we calculate the data for the returned instance. In case of multiplication, the data is a product of the right-hand side and the left-hand side. In case of subtraction, the data is by subtracting the right-hand side from the left-hand side. In addition to the data field, we also need to correctly set the operation field to the corresponding op enum. Let's also test the implementation of the multiplication and subtraction operations. Here V4 is equal to V3 minus V2, and the expected data should be 0.5. Then V5 is equal to V4 times V2. That will be 0.5 times 0.3 equal to 0.15. We verify if the data from V5 is equal to 0.15. The unit test passed. That means our implementation of the multiplication and the subtraction operations are correct. In addition, that also proves that a single value instance can be shared among multiple math operations. Similar principles apply when implementing the tanh-edge operation, but it is defined as a method of value. Here, we calculate data of the returned value instance as the tanh-edge of the data from the operand instance. The op field of the returned value is set to tanh-edge. Once again, we will validate the implementation using a unit test. Here, V6 is by invoking tanh-edge on the V5, and we verify if the data from V-edge is equal to the tanh-edge of 0.15. It would affirm that the tanh-edge operation is functioning as expected. That concludes today's coding session. In summary, we successfully implemented various mathematical operations and utilities for our neural networks in Rust, including add operation, multiplication, tanh-edge, and subtraction operations. We ensure the correctness of our implementations with unit tests. We also adopted a new type pattern by wrapping value underscore with the smart pointer reference count to make value lightweight to clone and shareable. Looking ahead, our future work involves implementing the topological sort and the backpropagation algorithms. Subsequently, with this in place, we will build a multi-layer perceptron. The code written today can be found on GitHub, and I have provided the link in the description below. Thank you for spending your time with me today. See you in the next session of our Rust journey to build a neural network.